welcome to all in the lecture series of functional analysis. Now in this lecture we see the theorem about the continuous mapping. So the statement of the theorem is, let capital X and capital Y be the metric spaces and capital T from X to Y a continuous mapping. That is we have to given, and now we have to show that the image of a compact subset capital M of capital X under the mapping T is compact. That is we have to show. So we start the proof. Given capital X and capital Y are metric spaces, also capital T from X to Y is a continuous mapping. That is we have to given. Now we have to show that the image of a compact subset of capital X under the mapping T is compact. Let capital M be a compact subset of capital X. That means here, as capital T be the mapping from capital X to capital Y, and capital M is a subset of capital X. As capital M is a subset of capital X, then T of M, that is the image of M under the mapping T, it is a subset of Y. Now here we have to given that this capital M is, here we have to given that capital M is compact, that is we have to given. Again we have to given that this mapping capital T is continuous, that is we have to given. And now we have to show that its image, that means as M is compact, then its image, that is T of M, we have to show that this T of M is compact. To show that the image of capital M, we have to show that the image T of M of capital M under the mapping T is compact. Now to show that T of M is compact, that means we have to show that it is sequentially compact. We have to show that T of M is sequentially compact. To show that it is sequentially compact, that means we have to show that every sequence in T of M sequentially compact. To show that T of M is sequentially compact, that means we have to show that every sequence in T of M contains a convergent subsequence. That is to show that every sequence in T of M contains a convergent subsequence. Now here we have to show that every sequence in T of M contains a convergent subsequence. To show that it is true for every sequence, so we start with any arbitrary sequence in T of M. Let sequence yn be any sequence in T of M. As it is a sequence in T of M, that means each term of this sequence is the element of T of M. That is, for all n, each yn is the element of T of M. And T of M, it is the image set of capital M under the mapping T. That means it is equals to the set of all y such that y equals to tx for some x belongs to capital M. This is the set T of M. Now for each n, yn belongs to T of M. It means that for all n, this yn, it is equals to txn for some xn belongs to capital M. And therefore here, as the sequence yn is like this, sequence yn, it is equals to the sequence containing the terms like this, y1, y2, y3. The another term is yn and so on. But here this y1, it is nothing but tx1, y2 it is equals to tx2, y3 it is equals to tx3. Another term is yn, that is equals to txn and so on, where each xi is the element of capital M for all I equals to 1 to up to so n and so on. Now using all these xi, we get a sequence. And this is the sequence xn. We get a sequence xn. Now for all I, each xi is the element of capital M and therefore it is a sequence in capital M. Now using all these xi, we get a sequence xn, and now this sequence is in capital M. As it is a sequence in capital M, and we know that capital M is compact, and as it is compact, that means it is sequentially compact. As capital M is compact, imply capital M is sequentially compact. Capital M is sequentially compact, and the definition of sequential compactness is that every sequence contains a convergent subsequence. Therefore, thus by definition of compactness or sequential compactness, sequence xn contains a subsequence say xnk. We give it the name, suppose that subsequence is xnk, which is convergent, say such a that xnk converges to x, and this x, it is the element of capital M. xnk converges to x and x belongs to capital M as nk goes to infinity. That means this xnk is a convergent sequence. This xnk converges to the point x, and x is the point of capital M. That means xnk converges in capital M. This is the definition of sequential compactness, and as here we get that sequence xn, it is a sequence in capital M, but capital M is given compact, means it is sequentially compact, and the definition of sequential compactness is that every sequence contains a subsequence which is convergent in that set, and therefore the sequence xn contains a subsequence, that subsequence is xnk, such that xnk converges to x and x is the element of capital M as nk goes to infinity, xnk goes to x. Now after this here, as this sequence xn, it is the sequence in capital M, and therefore here the corresponding sequence, that is the sequence yn, and it is nothing but the sequence txn. Now txn, it is a sequence in T of M, and therefore here as xnk, which is a subsequence of the sequence xn, Thus, thus the sequence Txnk. Now Txnk is a subsequence of the sequence Txn in T of m. Txnk, it is a subsequence of the sequence Txn in T of m. Now we have given that T is continuous. As here we have to given that T is a continuous mapping, as capital T from X to Y is a continuous mapping. Now here we apply the theorem for continuous mapping is that the statement of that is, let capital X and capital Y be metric spaces, capital T from X to Y is continuous at x naught belongs to capital X. The mapping capital T from X to Y is continuous at the point x naught belongs to capital X if and only if xn converges to x naught, implies that Txn converges to Tx naught as n goes to infinity. That is the statement of the theorem, that when x and y be the metric spaces, T be the mapping from x to y, then T is continuous at a point x naught belongs to capital X if and only if xn converges to x naught, implies that Txn converges to Tx naught as n goes to infinity. Now using this equivalent condition for continuity of T, here we have to given that the mapping T is continuous, and therefore by using this equivalent condition for continuity, here as we have that the subsequence, that is xnk, that converges to x as nk goes to infinity. Xnk goes to x, and now our mapping T, which is from x to y, it is continuous, and therefore here Txnk converges to Tx as nk goes to infinity. Now Txnk converges to Tx, and we know that x is the element of capital M. Therefore Tx, that is the element of T of M. Now here combining this equation, if we give it the equation number 1, we give it the equation number 2, then from equation 1 and 2 we get, here Txnk converges to Tx, and Tx, it is the element of T of M. That means here for the sequence yn, that is equals to the sequence Txn in T of M, we get a subsequence Txnk in T of M such that Txnk converges to Tx, and it is the element of capital M as nk goes to infinity. That means the sequence yn has a subsequence which converges, that belongs to T of M. Sequence yn has a subsequence Txnk which converges in T of m. But here, as the sequence Yn is any arbitrary sequence in T of m, and this arbitrary sequence in T of m contains a subsequence which converges in T of m, implies that every sequence in T of m contains a subsequence which converges in T of m. Here we can write as sequence Yn is any sequence in T of m. Thus we get any sequence Yn in T of m contains a subsequence which converges in T of m, and it implies that T of m is compact, and hence the proof that the image of a compact set under the continuous mapping is again compact, and hence the